We will discuss the properties of hyperbolic functions, as well as their connections to differentiation and integration. First, we might wonder why we need to learn so many different types of functions. In fact, these functions can sometimes serve as an intermediary tool to assist in calculations. For instance, when evaluating a certain indefinite integral, the integrand itself may have no connection to hyperbolic functions. However, when we perform u-substitution, setting the variable u in terms of a hyperbolic function can make the indefinite integral much easier to solve. We will demonstrate this purpose and motivation in the final example. Through the exponential function, we can define the hyperbolic sine function and the hyperbolic cosine function. The hyperbolic sine function is defined on the second line, while the hyperbolic cosine function is defined on the last line. Hyperbolic sine and hyperbolic cosine functions satisfy identities similar to those of standard sine and cosine functions, as listed on the screen. This screen discusses the differentiation formulas for the hyperbolic sine and hyperbolic cosine functions. The differentiation formula for hyperbolic sine is displayed on the second line. By applying the chain rule, it is easy to obtain that the derivative of hyperbolic sine is equal to hyperbolic cosine. Similarly, the last line shows that the derivative of hyperbolic cosine is equal to hyperbolic sine. This example requires simplifying the mathematical expression on the second line to t over 2 for any positive number t. First, we differentiate both sides with respect to the variable t. The first term on the right side of the equal sign applies the product rule for differentiation, while the derivative of the second term is explained as follows. To differentiate the second term mentioned above, we need the fundamental theorem of calculus, as displayed on the second line. There, the lower limit of integration is an arbitrary constant, while the upper limit of integration u is a function of t. According to this theorem, the derivative of the aforementioned second term is shown on the last line. After differentiating the above two terms, we obtain the first equality on the screen, which utilizes the facts that the derivative of hyperbolic sine is equal to hyperbolic cosine, and the derivative of hyperbolic cosine is equal to hyperbolic sine. The second equality then uses the identity hyperbolic cosine squared minus hyperbolic sine squared equals 1. After further algebraic operations, we arrive at the final constant of 1/2. Therefore, the original function is t over 2 plus a constant c. To solve for the constant c from the previous page, we simply substitute t equals 0. From the calculations on the second and third lines, we obtain that the constant c is equal to 0. Therefore, it is proved that the original function can be simplified to t over 2 when t is positive. By analogy with standard trigonometric functions, we can define the other hyperbolic functions. For example, just as the standard tangent function is the sine function divided by the cosine function, the hyperbolic tangent function is defined as the hyperbolic sine function divided by the hyperbolic cosine function, as shown on the third line. The remaining three hyperbolic functions can be defined similarly, as shown on the screen. This screen displays the differentiation formulas for these four hyperbolic functions. Their proofs can be easily obtained by applying the differentiation methods we previously learned. We will specifically prove the differentiation formula for the hyperbolic tangent function on the next page. The first equality is simply the definition of the hyperbolic tangent function. The second equality applies the quotient rule for differentiation. The third equality utilizes the facts that the derivative of hyperbolic sine is equal to hyperbolic cosine, and the derivative of hyperbolic cosine is equal to hyperbolic sine. The next to last equality uses the identity hyperbolic cosine squared minus hyperbolic sine squared equals 1. Finally, The last equal sign is obtained by using the reciprocal relationship between the hyperbolic cosine and hyperbolic secant functions. This theorem lists the inverse functions of three hyperbolic functions. Special attention must be paid to the domains of these inverse functions, which require careful discussion. We will only prove the inverse function of hyperbolic sine on the next page. Let y equal inverse hyperbolic sine of x. Then hyperbolic sine of y equals x. The definition of hyperbolic sine is displayed in the middle expression of the second line. Thus, we obtain the first mathematical expression on the third line. Next, multiplying both sides by e to the power of y yields the first mathematical expression on the fourth line. Letting z equal e to the power of y, the first expression on the fourth line can be rewritten as a quadratic equation in z, namely z squared minus 2x z minus 1 equals 0. Therefore, solving for z gives e to the power of y, as shown in the second expression on the fourth line. The second to last line explains that e to the power of y must take the positive sign. Finally, taking the natural logarithm of both sides yields the inverse function formula on the last line. This theorem lists the inverse functions of the other three hyperbolic functions. As before, special attention must be paid to the domains of these inverse functions, which require careful discussion. This screen lists the differentiation formulas for the inverse functions of these 6 hyperbolic functions. Since the explicit formulas for these inverse functions can be obtained from the previous 2 theorems, it is not difficult to derive the differentiation formulas on the screen by simply applying the differentiation methods we previously learned. Here, we will only compute the differentiation formulas for the inverse functions of hyperbolic sine and hyperbolic cosecant on the next 2 pages. First, we will compute the differentiation formula for the inverse function of hyperbolic sine. According to the previous theorem, the formula for the inverse function of hyperbolic sine is already known and displayed on the second line. By applying the chain rule, we can derive the differentiation formula shown on the last line. Next, we will use implicit differentiation to compute the differentiation formula for the inverse hyperbolic cosecant function. Let y equal inverse hyperbolic cosecant of x. Then hyperbolic cosecant of y equals x, which means hyperbolic sine of y equals 1 over x, as shown on the third line. According to implicit differentiation, differentiating both sides yields the mathematical expression on the fourth line. It is then rewritten in terms of dy/dx, displayed on the second to last line, where the second equal sign is obtained by using the identity hyperbolic cosine squared minus hyperbolic sine squared equals 1. Since hyperbolic sine of y equals 1 over x, hyperbolic cosine squared of y equals 1 plus 1 over x squared. Taking the square root, then, gives the mathematical expression after the second equal sign on the second to last line. After algebraic simplification, we arrive at the differentiation formula on the last line. This example involves computing the indefinite integral on the second line. Using u-substitution, we set the variable x equal to constant a multiplies hyperbolic sine of u, as shown on the third line. The equality on the fourth line represents the indefinite integral after substitution. On the second to last line, the first equal sign is obtained by using the identity hyperbolic cosine squared minus hyperbolic sine squared equals 1, which simplifies the integrand to the constant 1. Integrating constant 1 then yields the mathematical expression after the second equal sign. The third equal sign uses inverse hyperbolic sine to express variable u back in terms of x. The last line applies the previously established inverse hyperbolic sine formula, completing the calculation. This example illustrates that the hyperbolic sine function can serve as an auxiliary tool for integration, even though the integrand itself bears no relation to hyperbolic sine. We simply define u in the substitution using the hyperbolic sine function. After integrating, we obtain the inverse hyperbolic sine function, which can then be completely eliminated using its explicit logarithmic formula. Ultimately, the purpose is merely to use the hyperbolic sine function as an intermediate tool to evaluate the indefinite integral.